Okay, so I guess let's get started. So, so today this lecture we're going to discuss a few small stuff that are remained that are kind of like left from previous lectures, and then we're going to move on to unsupervised learning. So, so I guess the first thing is that recall that last time we talked about implicit regularization of the noise. And we mentioned that in certain cases, you can prove that the regularizer prefers the noisy SGD, noisy GD prefers smaller this quantity R theta, which is defined to be something like the trace of the Hessian. So, and in the first part of this lecture, I'm going to spend probably 10 to 15 minutes to briefly discuss why this is a reasonable thing to try to minimize or try to kind of like regularize. So why the trace of the Hessian is some meaningful quantity, or but this part wouldn't be exactly kind of like rigorous because you have to do some approximations, so on and so forth. But I'm just going to do some kind of like a somewhat heuristic derivation to justify why something like the Hessian would be useful for us to regularize. So I guess the thing is that how do we, what is the Hessian, right? What is the Hessian? And maybe actually I should write, I will hide, this is the Hessian on the empirical laws. So maybe for simplicity, let's only consider one data point. So, and let's say, suppose f, let's denote f to be f comma theta. This is the, I guess, maybe I should say f theta x be the model output. And let L Fy be the loss function. Then what you can do is that you can compute. So then the L theta in this case is just the L of f theta xy, right? So in this case, then we can compute what the Hessian is. So the Hessian, maybe let's call it L hat, just to be consistent in terms of notation. The Hessian is the gradient of the gradient. Now, what's the gradient? If you use chain rule, what you're going to get is that you get L, the partial L over partial F times partial F over partial theta. So this is nabla, the derivative with respect to, so this is a scalar function. L is a function of F, but this is a very simple function, right? Because L is a scalar, F is a scalar. So this is a scalar and times the gradient of f theta at x. So, and now you are taking the gradient of a product of two quantities. One is a scalar and the other is a gradient. And then you can do chain rule. What you're going to get is that you first, for example, do the gradient with respect to the first part. What you get is, let me see what you get from the first one is that you have L, the second order derivative with respect to f, and then you do the chain rule, you get this f theta x. So this is gradient with respect to theta times gradient f theta x transpose. And this is the, in some sense, so this part is the gradient of this, and this part is copying, I guess, this is copying from here in some sense. But I guess, this is something that you can verify offline, like if you do all the kind of like, if you look at all the coordinates and do all the calculation. And then you can also do the chain rule for the other part. So what you can get is the dl over df times the second order derivative of the model theta at x. The matrix of dimension p by p, if p is the number of parameter, and this is a scalar, this is a scalar, and this is a vector, this is a vector. So the whole thing is a P by P matrix. So when you have suppose your loss, so this is a general formula which is just rigorously true, and suppose the loss function is LF y is equals to, for example, 1/2 times y minus f squared, then this formula becomes, what is the second order derivative of this loss function with respect to f? This function is a quadratic function of f, right? The loss function is a quadratic function with respect to f, and the leading term is f squared. So the loss that the second order derivative with respect to f is 1. So this is equals to 1 times gradient theta of f times the gradient of f theta transpose. And then the first order derivative will be, with respect to f, will be f minus y times the Hessian of theta x. So this decomposition is often called, so what we can see is that this is a convex term. This is a PSD term, sorry. This is PSD because it is the outer product of a rank 1 matrix, and this is non-negative. And this is not necessarily PSD. So the Hessian may not be PSD in general, of course, right, because you have a non-convex function, but one of the term is PSD. And if you have it in general, if you have a convex loss function, the first term, so in general, this is called, I don't know why this is called this, but it's called Gauss-Newton decomposition. I think it must have something to do with these two famous people at some point, but it's called Gauss-Newton decomposition. And in general, the first term, this is always positive for convex loss function. But I guess by loss function, I really mean the literally the top, either quadratic loss or kind of like or cross entropy loss. They're all convex, right? So this term, in almost all cases where we study the first term, this is non-zero. So the first term is PSD. PSD. And empirically, people found that the second term in most of cases is small. So there could be multiple reasons for this. So empirically, the second term, f minus y, this is generally smaller. And one of the reasons could be that, at least when you are at a global minimum, this term is 0. So when theta is at a global mean, so meaning f theta x is equals to y, right? So a global mean would fit the data exactly. So in this case, then this term is actually literally 0. So f minus y 0. So this could be one reason why empirically the second term is relatively small. Of course, this is not always true. It's not always true you can fit the data at any point. But somehow people found that the second term, is somewhat smaller than the first term. So if you don't care about anything if you don't care about a very nuanced kind of quantities, but the Hessian in the first term is a reasonable approximation for the Hessian. Of course, in certain cases, you do care about the nuances. For example, when you care about whether this function is convex or not, you should talk about even any non-negative eigenvalue would make it non-convex, right? So then the second term becomes important. But if you just care about a trace, then the second term is not that important. So that's the rough intuition. And now suppose you ignore the second term. This is a big assumption, but suppose ignoring the second term, then we can see what's the trace of the Hessian. Second term. So the trace of the Hessian, for whatever reason, right? For example, you can ignore it just because it's empirically small, or you can ignore it because you are at a global minimum. But suppose you ignore the second term, then the trace of the Hessian and theta is approximately equals to this derivative is equal to y, which is probably 1 if you have square loss times the trace of this transpose, which is equals to some scalar times the true norm of the gradient. So you can see that by minimizing the trace of the Hessian, you are minimizing the L2 norm of the Lipschitzness with respect to the parameter. So this is so minimizing the trace of the Hessian is somewhat similar heuristically, minimizing Lipschitzness of the model with respect to theta. And I think, so why minimizing the Lipschitzness of the model with respect to theta is useful. Actually, first of all, this is indeed useful. If you just explicitly minimize this, people have found that empirically this is useful. And why this is useful, if you allow some heuristics, you can also say that this is very similar to the minimizing the Lipschitzness of the model output with respect to the hidden variables. I think this is something that we discussed probably like a few weeks ago when we talk about the outlier margin. So recall that if you have a neural network theta, which consists of, for example, a bunch of layers, suppose you have a deep network with a lot of weights, and then the derivative of the model with respect to some layer I, this is equals to the derivative of the model with respect to the layer above it times the layer, let me see, so this is hi plus 1 times hi minus 1 transpose. So this is the so-called, okay, I guess now I remember it's called Haibin rule. But it's actually just literally a simple chain rule. In the neuroscience, this is called Haibin rule. But technically, it's just a real chain rule. You want to take the derivative with respect to the parameter, and the parameter kind of come into play that depends on hi minus 1 and hi plus 1. And sorry, this is hi. So what is h? So here hi plus 1 is w times hi. Right. So this is the ith layer, and this is the pre-activation of a plus 1 layer. I guess maybe technically I should call this hi prime just so that I can distinguish it from post calibration. But I guess you get the point. The point is that if you take the derivative with respect to a parameter, it's actually very closely related to the derivative with respect to a hidden variable and the norm of the hidden variable hi. Right. So this means that the Euclidean norm, if you view the matrix and it's a Frobenius norm of this, is equals to 2 norm times the hi 2 norm. So minimizing the Lipschitzness with respect to the parameters is similar to minimizing the Lipschitzness with respect to hidden variable. I think this is something we have discussed before when we do the all-layer margin, right? So then when you talk about derivative of the hidden variable, then this is kind of like all-layer margin. I guess you are maximizing the all-layer margin. Because all-layer margin is bigger if you have more Lipschitz model. You have a larger all-layer margin. So none of these steps can be made 100% rigorous. Some of the intermediate equations I've written are exactly true, but I don't think all of these steps can be made completely rigorous. But sometimes this is probably the nature of neural networks, right? You cannot be 100% precise just because things don't match exactly. But I think the intuition is really just that the Hessian, the Hessian relates to the Lipschitzness of the model with respect to parameter, and the Lipschitzness of the model with respect to parameter relates to the Lipschitzness of the model with respect to hidden variables, which is kind of like captured by outlier margin. Any questions? Okay, so this is the first thing about this is the remaining steps, the remaining remarks from the last lecture about the implicit regularization of the noise. And there's another thing I want to discuss, which is something in some sense, it's my omission. I forgot to provide the proof for one of the theorems that we discussed, I think 2 weeks ago, about the implicit regularization effect in the classification case. I think there we only basically at the end of that lecture, we only were able to kind of provide the theorem and the basic intuition. But we weren't able to really show the proof. The proof is very simple and short, like just a 1 page. I think it's very nice proof. So I really want to show it to you. So maybe let's discuss that in the next part. So I will remind you what the theorem was about. So guys, this is I think 2 lectures ago. So 2 lectures ago, we showed the following theorem. The theorem was something like, suppose you have maybe the context is that we have linear model, classification, and we have a gradient flow. We have infinitesimal learning rate. And we want to understand what's the implicit bias of the algorithm in this case. And the theorem that we had was that gradient flow converges to the direction of the max margin solution. In the sense that, so the margin of your iterate is converging to the max margin solution as t goes to infinity. So here Wt is the iterate of gradient descent at time t, of gradient flow at time t. So, and gamma is the normalized margin and gamma bar is the max margin, max normalized margin. I think at the end of the lecture, I think I discussed the intuition. The main intuition is that the cross entropy loss is really, basically you can do an approximation, and in certain cases, the cross entropy loss is an approximation of the max margin. So the main intuition, if you recall that lecture, I will just very briefly summarize this. So the main intuition is that if you do a bunch of kind of heuristical calculation, you can find out that the log of the loss is approximately equals to let's see. So log of loss is approximately equals to minus times the norm of W times the gamma W. So basically minimizing the loss is kind of like either you want to make the norm of W bigger or you want to make the margin bigger. So we did this in a very heuristic simplification, give you this. So that's why if you want to minimize the loss, in some sense, you are either trying to make the norm bigger or you're trying to make the margin bigger. And it turns out that you can actually control both of these two kind of forces, these two kind of like tendency. And if it's actually true that the norm is growing and the margin is also growing, both of them are trying to be big. And you can show that the norm grows, to infinity, and the margin grows to the largest margin. So that's the thing we're going to prove in this theorem. Any questions so far? And one of the key things that we discussed at that point was that the log sum exponential, and one of the key technique is that log sum exponential is kind of like the same as max. If your input is has a large scale. So today I'm going to provide the formal proof for this theorem, which is actually pretty, in my opinion, it's very elegant and simple. And we only prove for only the case when the loss function is minus exponential t, like the exponential loss. Recall that in that lecture, we also discussed that the logistic loss, even though it's called logistic loss, it's actually very close to exponential loss. So we only deal with exponential loss, which is kind of almost the same as the logistic loss. So the main feature is that as t goes to infinity, the loss goes to 0. So the t is supposed to be the margin, and when the margin is very, very big, then your loss is very small. So, and the idea is that we can consider the smooth margin. So the smooth margin is defined to be, I think in the lecture we defined the smooth margin to be, let me find out the, I guess I'm looking at. Okay, so the smooth margin is defined to be the following. So consider the smooth margin. So the smooth margin is defined to be the log of the empirical loss over the 2 norm of W. So recall that we have tried to, minus log. So we have established this equation last time during the intuition, and that actually motivates the use of the smooth margin. You can see that the smooth margin is basically supposed to be approximately equals to the margin, gamma of W, right? If this approximation is true. But it's not exactly equal to that just because this is only approximately equals to. So that's why we work with this smoother version, which is in some sense like almost the same as the margin, but just more kind of closer to the loss function L hat. And if you work with the smooth margin, you can show that the smooth margin is actually, I guess we have proved this in the last lecture. So the margin is actually bigger than the smooth margin. So I guess maybe let's just write out exactly what this is. This is minus log sum of an exponential minus yi times W transpose xi over the norm of W. And you can show that the margin is larger than a smooth margin. That's because we can replace each of these terms by the minimum, right? This is just because yi W transpose xi is less than gamma W times the norm of W. Sorry, this is larger than this. So the smooth margin is supposed to be something close to the margin, but smaller. So that's why it suffices to show that the smooth margin, gamma tilde W, converges to gamma bar. WT converges to gamma bar. This is because you have this sandwich thing, right? So you know that the gamma W is always than gamma bar. So basically, the smooth margin is sandwiched between. So if the smooth margin converges to gamma bar, then gamma W has to converge to gamma bar because there is no way for gamma W to go beyond gamma bar. Okay, so now basically this is what we're going to do. We're going to prove that even the smaller value, the smooth margin, is going to converge to gamma bar. So then the larger value will also converge to gamma bar. So and the proof is actually also pretty simple. So we basically show that we'll show the gradient flow will increase this quantity, the log of the WT, log of the log loss, because it decreases, intuitively because it decreases L hat WT. So let's do this formally. So concretely, because I think this statement itself, right, it will increase the minus of the log loss. That's kind of like almost obvious because the loss itself is going to decrease. But how much it increases requires some kind of mathematical derivation. So concretely, suppose recall that the change in W is minus gradient LWT. This is the definition of the gradient flow. Then what you have is that the derivative with respect to T of the changes in the minus of the log loss is equals to, so how does this change? This you take the chain rule, right? So you first look at how does the loss depends on W, and then you look at how does W change, and how does the loss depends on W. So that's the derivative of the, so then this is like a derivative of this, which is minus you use the chain rule again, so you get L of WT is the chain rule for the log, and above you get the gradient of L hat WT, and then you have W dot T. And recall that W dot T is really the gradient of the loss function. So basically, up to a sign. So basically, you get the gradient of the loss function 2 norm square over L of WT. And this is bigger than 0. So this shows that this minus log loss is going to increase as T goes to infinity. But the important thing is how fast it increases is this quantity. This is something we're going to use. This whole thing is increasing is not surprising because the loss is decreasing. But this we also want to know how fast this is increasing. And by the way, you can actually, I think it's useful to use this because we're going to compare it with. You can also write this as this equals to this, just because the nabla L hat is just equals to W dot T. Okay, so now with this, what we can do is that we can control what eventually after T step, what happens with the log loss. So what you get is that minus log L hat WT is equals to minus log L hat W0 plus the integral between 0 and T of the derivative of this quantity. dt minus. So, and this is going to be using the equation above, you get that this log W0 plus the integral of W dot T 2 norm square over L WT. Okay, so we basically now know how fast, how large is the log loss, right? So recall that what we care about is this quantity. What we care about is this. And how does this go to gamma bar as T goes to infinity? And we have already deal with the numerator, and we just have to kind of like we know how does this. Someone know how does this change for the numerator, and we have to again another thing is that we have to kind of like try to understand the denominator, right? So the denominator, you have to normalize this by the norm of W. So so basically, next thing is that we're going to deal with this term and compare it with the normalizer norm of W. So what you do is that you look at the W dot T square. This is bigger than W dot T times W star. Recall W star is the direction of max Martin solution. This is just by Cauchy-Schwarz, right? So the inner product of two vectors is less than the norm of one vector times the norm of the other vector, and the norm of the W star is assumed to be 1. So then we plug in the definition of W dot minus gradient L WT W star. And then we plug in the true definition of the nabla L. So like we plug in a derivation for the nabla L. So this equals to yi times exponential minus yi x W transpose xi times xi and times W star. And then this is a vector, this is a scalar, this is a scalar. So basically you can just take inner product of these two and multiply the scalar. So this will be equals to, I guess there's no minus here because there's another minus in the gradient which cancels. So then this is equals to sum of yi times exponential minus yi W transpose xi times W star times xi. I guess maybe let's write this. So W star transpose xi. So, and this, we can see that this is the margin of the max margin because W star is the max margin solution. So this is always bigger than the max margin. So this is larger than gamma bar times, I guess, let me finish it and let me explain. Because yi W star transpose xi is bigger than gamma bar. This is just because gamma bar is the margin of W star. So that's why every data point has a bigger margin than the margin of the data set. Gamma bar is defined to be minimum over all data sets. So, and then this is equals to gamma bar times the loss. So with this, then we can proceed by dealing with this term to further lower bound how kind of control how fast you grow. So with this, you get log L hat WT is larger than minus log L hat W0 plus so maybe just one moment before I use this. Let me just try to interpret what this is really doing. So this, let's see. So So in some sense, as a remark, what this is really doing is that, so WT, we show that WT, so we show that WT is correlated with W star. Right, that's what we are showing, right? So we are showing that the W dot T times W star is bigger than a non-negative quantity. And how correlated it is depends on, and the correlation depends on gamma bar and the loss. So in some sense, and because you are correlated with W star, it means that you cannot, W dot T itself cannot be too small. So and also this is another thing we got, right? So W dot T is not too small, at least compared to the loss. So what this is saying is that, if the loss is not too small, then you have to make some changes in your W. And if you have to make some changes in your W, then you have to make some changes in the log of the L hat WT. So basically, if the loss is not small, then your log of the loss needs to increase. The minus log of the loss needs to increase. So it's a little kind of like counterintuitive in some sense. But I guess, so what we do next is that let's control this term, additional term that is circled here. So this term, if we use the equation we got this is larger than gamma bar times you cancel out one of the log, or you can use this for one of the, there's a power 2 here, right? You can use the equation, maybe let's get this equation 1 for one of these occurrences of W dot T. So then you get, you are left with 1, and then you got gamma bar and L hat. L hat got canceled with the denominator, and gamma bar is put in the front. So you get this. So basically, I'm applying equation 1 for one of the W dot T to norm. And then you can use a triangle inequality. So this is by 1. Use a triangle inequality to say that this is larger than the integral of W dot T to norm squared dt. Sorry, my bad. This is replacing the integral with the norm, and you get gamma bar times the norm of WT. So I guess, next you're going to see why we care about all of this, because we care about this because now you can control how fast L hat, this log loss is improving compared to how fast the norm of W is improving. And this is what we really care about, because fundamentally we care about the ratio between them. This is the definition of the soft margin or the smooth margin. So this means that the ratio is getting closer to gamma bar, right? So this term is a constant, and this term is something that becomes closer to 0 as t goes to infinity. So WT goes to infinity as t goes to 0, as t goes to infinity. That's why this term here converges to 0 as t goes to infinity. So that's why if you take the limit when t goes to infinity, we'll get that this smooth margin, right? So recall that this ratio is the smooth margin, is converging to gamma bar. So in other words, the limit t infinity gamma tilde WT is equals to gamma bar. Maybe here you only get negative, and then you use the other way to show that, and you also know that, okay, so we also know gamma bar is larger than the margin of any W, because gamma bar is the max margin, and which is larger than WT. And then you can show that the limit is actually equal to gamma bar, exactly. So we're done. Any questions? Okay, so I guess with this, we basically concluded our section about implicit regularization. So I guess just to very quickly, briefly wrap up. So this is the end of the section about implicit regularization. And we have talked about a bunch of things like initialization. So small initialization prefers certain kind of solution. Typically, small norm solution prefers, small norm solution. And we are actually, in one of the cases, we also show that, you can have an interpolation between small initialization and large initialization. So in that case, you can show the implicit bias for any initialization. And we also talk about the classification problem. So where you get the max margin. So this is where you get max margin solution. And we also talk about the noise. So in all these cases, it's kind of like you have something about your optimizer that is only designed for optimizing faster in some sense, right? But somehow as a side effect, you get implicit regularization effect. Okay, so any questions? Okay, so if there's no questions, let me move on to the final part of this lecture, of this course, which is more about unsupervised learning, representation learning, so on and so forth. So in this lecture and the last two lectures, we still have so basically in the next 2.5 lectures, we're going to talk about unsupervised learning. There are not that many theoretical work about unsupervised learning. Of course, there are a lot of very amazing empirical works these days, but not that many theoretical work. So what I'm going to do is that I'm going to start with somewhat kind of classical approach a little bit. So for this lecture and the beginning of the next lecture, maybe a good portion of the next lecture, I'm going to talk about the classical approach. Classical theoretical approach. So there are many approaches, before, like for example, the most empirically probably before deep learning, the best empirical approach would be probably like you do latent variable models with EM, expectation maximization. But I'm going to, for those kind of EM algorithms, there are very little theoretical analysis, and even there is analysis is kind of like a special case, and it's not clear whether they can be extended to very complex case. So what I'm going to talk about is a different line of research which use the so-called moment method. So these kind of methods, don't necessarily work very well for empirically, but they have very good. You can analyze them in a very clean way, and these kind of mathematical techniques are also useful for many other cases. So I think it's worth spending one lecture to talk about this approach. And it used to be the case that actually around probably 2012, 2013. At that point, I think the theoretical community thought that this might be the new thing. This could be the new thing that you can both analyze and empirically work. It turns out that the analysis part, got developed very well, but the empirical part, is doing okay, but not kind of like good enough to replace the EM algorithms, at least not enough to replace them completely. So and then I'm going to talk about some of the more modern work with deep learning. With deep learning, like for example, self-training or contrastive learning. So these are basically analysis in the last 1 or 2 years about some of the new algorithms in deep learning. So I'm going to spend probably the last lecture and the last 1.5 lectures on this. Okay, so that's the plan for the next 2.5 lecture. And so today I'm going to talk about a classical approach, right? So, and by the way, another kind of general comment is that, in my opinion, this unsupervised learning seems to be the core for many things, right? So this also relates to, for example, semi-supervised learning, where you have some unlabeled data together with labeled data. And this also relates to unsupervised domain adaptation. And my personal opinion is that all of these questions, right, what really you care about is really, in both of these questions, what you really care about is how do you leverage unlabeled data. So in some sense, they all reduces to unsupervised learning, in my opinion. Okay, so now let's get into something more concrete. So let's have some setup. So this is the setup. This is with latent variable models. So we are interested in those kind of latent variable models, especially in a classical approach. So the formulation is that you have a distribution P theta parameterized by theta. How is parameterized theta? That would be, there are many different ways, which I'm going to introduce a few of them. But every parameter decides the distribution p theta. And then you are given unlabeled examples, right? There's no labels anywhere, right? So you're given examples, x1 up to xn. They are sampled IID from this distribution p theta. And your goal is to recover theta or learn theta from the data. So that's the formulation. And p theta can be described, as a latent variable model, or can be, or typically is described by a latent variable model. So every theta describes a generative model in some sense. So for example, I assume you somehow know, roughly speaking, what latent variable model is from CS229. But let me give some examples. For example, mixture of Gaussian. This is one of the probably the most studied distribution in machine learning. So the assumption is that in the most general sense, the theta is, so the parameters are describe a bunch of things. So let me write it down first. So you have a bunch of vectors, k vectors, and a bunch of probability numbers. So each of these mu I is, in dimension d, is the mean of the component. And p1 up to pk, this is a probability vector. In the simplex, right? Let's call it data k, a simplex in k dimension, which is basically a set of vectors with norm equals to 1 and non-negative, and in dimension k. Right, so p1 up to pk is a probability vector over k items. And right, so and given these parameters, what's the model? How do you generate? So this is my parameter, and how do you generate data? So it's mixture of Gaussian. So intuitively, you just you want to model the case where you have, for example, something like this. You have several clusters of data, something like this. I guess you don't see the color in the data. You just see the raw inputs. The color is just to indicate which Gaussian it comes from. So mathematically, you say that you sample x from p theta by you first sample some I, the cluster ID, from a categorical distribution defined by p. So I is between I can take values from 1 to k, and then given the ID, the cluster ID, you sample a Gaussian with mu sub I, and then some covariance, let's say identity. So actually the covariance can also be a parameter you want to learn. But here for simplicity, I just assume all the Gaussians have the same covariance just to make the everything easier. So this is a latent variable model. So where I is the latent variable. This is something you don't observe in your data. You only observe x. But given the latent variable, you can generate the data. So basically, there are two parts where you first generate latent variable and then you generate data under the hood. And then many other approaches which I'm going to define probably mostly when I'm going to use it. So HMM, the hidden variable model, hidden Markov model. I guess if you take some NLP class, probably you have seen these kind of things, or ICA, independent component analysis. This is also something I think covered in CS229. And so there are many other kind of like latent variable models, space nets, so on and so forth. So this is the family of questions we're going to study. And now let's talk about the approach. So the approach, maybe before that, any questions? Okay, so the approach we're going to study is the so-called moment method, which is actually pretty powerful. as an approach, there are some drawbacks, which make it empirically a bit less appealing. But the approach itself, if you don't care about certain kind of like aspects, then it's actually pretty powerful. This is called moment method. I think this method is proposed by actually an economist, or actually a few economists to understand data from economy, from economists, from like I think Michael, I don't know, like some kind of like so the original source is definitely not machine learning, but then people use this for machine learning these days with actually pretty complicated approach. Actually, even though I think actually I think I misspoke. The very original proposal of this moment method actually probably dates back to 19th centuries by some statisticians. So and then actually some economists even got the Nobel Prize by generalizing these moment methods to kind of like something like what we are discussing right now. So anyway, so let's see how does this work. So I'm going to just only kind of like I'm going to walk you through this kind of method by showing examples. So let's do the first example. So first example, let's talk about mixture of two Gaussians. So you just have two Gaussians, and I think and also let's say k is 2, right? So and then let's also assume P1 and P2 are just a half. So these two Gaussians have the same probability. So they have the same marginal density. And also without loss of generality, we can assume the mean is the average of the mean is 0. So basically they are just symmetric around origin. This is in some sense without loss of generality because which point you choose as the origin wouldn't really matter that much. So so then mu1, you can write mu1 as, so let mu to be equals to mu1, and then mu2 is equals to minus mu. So basically, we only want to learn one parameter vector, which is mu. And the data comes from this mixture of two Gaussians. Right? So one Gaussian is mean mu and covariance identity. Another Gaussian is mean minus mu covariance identity. Right. So, and the moment method, so the general approach for moment method is the following. So first, you estimate moment of x using empirical samples. I'm going to define what exactly a moment really means. Moment really means I guess, depending on whether you have any backgrounds, I can define what moment really means. And then what you do is you recover parameters from moment of x. And by moment, we really mean something like this. So the first moment just means the average of x of the data. So the first moment, okay, and let's try to do this, for this particular example, right? So if you do the first moment, then the first moment is the expectation of x. And what is the expectation of x? There are two cases. One case is that you have a latent variable, which is 1, and the other case is the latent variable is 2. So you can look at the expectation of x for both of the two Gaussians, right? So with half the chance you come from the first Gaussian, and that's the case when I is 1, and half the chance you come from the second Gaussian. And when it comes from the first Gaussian, the mean is mu. So that's the definition, right? So you get a half times mu. And you come from the second Gaussian, the mean is minus mu. So you get minus mu, which is 0. So this means that there's no information about mu from first moment. not so good, right? So this is not our plan. Our plan is to recover mu from the moments, but from first moment we cannot really get anything. So then what you do is you go to the second moment. So the second moment is the expectation. Let's call it M2. Maybe I should call it M1 as well. So a second moment is M2. It's defined to be the expectation of the outer product of X with X itself, right? Oh, there's this expectation of X and X transpose. So why this is called the second moment? This is really, this is a matrix. Basically, you can see that M2ij is the expectation of xi, xj. So basically, this is expectation of the kind of like the product of two coordinates of the data, and you organize all of this into a matrix, and you call it M2. So, and if you compute the second moment, then you can see actually mu is, you can kind of see mu from it. So how do I compute the second moment? Again, the same thing with half of chance your X from the first Gaussian, with a half of chance your X come from the second Gaussian. And when it comes from the first Gaussian, so what's the covariance? What's the second moment of X under the first Gaussian? So this requires a little bit of calculation. So let's do that here. So suppose X come from a Gaussian with mean mu and covariance identity. And what is the second moment? Maybe let's have a different letter for this so that we don't call it X. Let's call it Z. So how do you compute this? So there are several ways. Where one way is that you just literally look at each of the coordinates and try to compute the expectation. That's perfectly fine. So here I'm going to be a little bit lazy. I'm going to write that this is equals to expectation of Z times expectation of Z transpose plus the covariance of Z, right? Because covariance of Z is equals to the second moment minus the outer product of the mean. And the mean is mu, so you get mu transpose, and the covariance is identity, so that's where we got mu transpose plus identity. And for the second, so basically you get a half times mu transpose plus identity. And for the second Gaussian, actually the moment is the same, just because mu and minus mu is the same if you square it. So you get a half times mu transpose plus identity. So eventually you get mu transpose plus identity. Okay, so now it looks good because at least mu seems to come from, mu is can be in some sense read off from the moment, right? So if you get the second moment, you subtract I, you can recover mu, right? So basically what you do is you say, you estimate M, but you don't necessarily know M2 exactly, right? So you estimate M2 by the empirical samples. So what's the empirical samples? So you define this empirical moment as the empirical second moment. And then you recover mu from M2 hat. By pretending M2 is the same as M2 hat is the same as M2, right? So for example, you can recover mu by how to do this. One way to do it is you can subtract I from M2 hat and then try to take the square root of it. And here I'm going to do one. So basically the key thing is that so how to recover, right? So let's do a warm up. So there are, I guess in some sense, to recover it from M2 hat, the first thing you want to make sure is that you can recover it from M2, right? So this is kind of like a premises. Can recover mu from M2, right? And we have argued that this is actually true because you can just subtract I from M2 and then take the square root. There's another way to do it, which is so another way, which is the spectral method. I'm going to introduce this here because it's going to be useful for the future cases. So how to recover mu from mu transpose plus identity? What you do is you take the top eigenvector of M2 is actually equals to mu over the norm of mu. Let's call this mu bar. So the top eigenvector of M2 is actually exactly in the direction of mu bar. So and this is something like, and also the eigenvalue is, the top eigenvalue is mu 2 norm square plus identity. And this is something like you can verify relatively easily, right? So because eigenvector of mu transpose is mu bar, and then eigenvector of mu transpose plus identity is the same. This is just because if you add identity to any matrix, you don't change the eigensystem. You don't change the eigenvectors. You only change the eigenvalue. The eigenvalue got incremented by 1. That's what happens when you add identity to any matrix. So you can see that from M2 you can recover mu, either using a simple subtraction and square root, or you can do this eigen decomposition. And this is the case actually. This is actually also corresponds to the infinite data case, because when you have infinite data, you can literally compute M2, because the average will be exactly equals to the population. So now the question becomes like, what if you don't have infinite data, right? You don't have M2, you only have M2 hat. So basically you need recover from M2 hat, basically using the same algorithm, on M2 hat. So basically you just use the same eigen decomposition on M2 hat, and you need this algorithm to be robust to errors. In the sense that if you have two matrices, M2 and M2 hat, they are similar, then applying this algorithm will give you similar answers, right? So if that's the case, then you get similar answers as if you computed on M2, so you get an approximate estimate for mu, right? And it turns out that this robustness thing is often okay, like at least in a qualitative sense. Like for most of the algorithms we're going to discuss, they are robust to some errors. So actually the most important thing would be this. So we're going to focus mostly on the infinite data case. So we're going to focus on infinite data case because most of the algorithms is robust to errors. So the error analysis part is important if you really publish a paper, but for the core idea, you don't have to really do the error analysis because most of the algorithms are reasonably robust. Okay. Any questions so far? Okay, so we have completed a discussion about this mixture of two Gaussians, and now let's deal with mixture of three Gaussians. And you can see that the point will be that you cannot just only use the first moment and second moment. You have to actually go to the third moment. and it will be make things a little bit more complicated. So maybe the general approach, just to is that you compute M1, which is the expectation of x, M2, which is the expectation of x prime, and M3. What is M3? What's the third moment? M3 is the expectation of x tensor x tensor x. If you're not familiar with this notation, so x tensor x tensor x, this is the third order tensor of dimension d by d by d. So and so let's say this is called t. So then t is the third order tensor, and the ijk entry of this tensor is equals to xi times xj times xk. Okay, so in some sense, like if you do so x tensor x is basically just a rewriting of x transpose, and x tensor x is defined like this. So, and you can also have like a tensor b tensor c. So suppose t prime is equals to a tensor b tensor c. Then t prime ijk is equals to, definition would be ai times bj times ck. So and so that's why in this sense, if you look at M3 ijk entry, then this is the entry of the ijk entry, which is expectation of xi times xj times xk. So basically every entry of this third order tensor M3 is the expectation of the product of three coordinates of the data. So, and you can do this even for M4 or M4 and M5, so on and so forth. So, and then you design algorithm. Maybe let's call it A, script A, that takes in the moment and outputs theta. So you want to recover from the moments the parameter theta. And then if you can do this, then the last step will be that you have to show A is robust to errors, and then apply A to the empirical moment. And what is the order of the moment? So this is in reality, right? So this is the final algorithm. So applying A to the empirical moment, that's the final algorithm. All the previous steps are kind of like the process of designing the algorithm. So, so basically, but what is the order of the moments you have to use, right? So do you need third order moment, fourth order moment? That depends on from how many moments you can recover the parameter theta, right? If from the first moment, second moment you can recover, then sure, 2 moments are fine. If you need 3 moments to recover, then you need M3. Otherwise, you probably even need M4. In some cases, indeed, we need M4. I guess I think even in your case that we're going to discuss, we need M4, the fourth tensor. Any questions? Okay, so I think I have only less than about about 15 minutes. So I'm going to show that let's talk about mixture of K Gaussians, and I'm going to show you that you actually need at least the third moment when the number of components is not just 2. And this is very typical. In most of the cases, you need at least a third moment. Actually, it's not very easy to find a case where second moment suffices. Like I have to think about which case second moment suffices for a while, and I found this like two-component mixture of Gaussian. In almost all other cases, that you need third moment. So let's assume again. Let's make it simpler. So let's assume that this is a mixture of Gaussians with a uniform mixture. So all the components have 1 over k probability to show up. So basically, you sample I uniformly from k, and then you generate x from Gaussian with mean mu I and covariance identity. This is the generative model for data. And alternatively, you can probably write x is sampled from this, the average of this k distributions. And what in all the follow-up, we are going to only do A and B. So we only do A and B. The step A and step B for all examples in the sequel, even including examples in the next lecture. The robustness, you can do that, but it requires too much kind of like mathematical jargon, which is not really needed for this course. So, and A and B is really the gist, is really the core thing that enables this. So, so now let's try to compute the moment, right? So, and see which moment is enough for us to recover. Again, let's compute the first moment. So this is, you have k possible cases, right? So each case arises with its probability k, probability 1 over k. So each cluster shows up with probability 1 over k. So condition on the cluster I, your mean is mu I. And take the sum of them. This is 1 over k times the sum of mu I. So clearly from the first order moment, the first moment you only know the average of the mean, you probably wouldn't be able to recover each of the mean. That sounds reasonable. So, and now let's look at the second moment. The second moment is I guess we still do this kind of like total law of expectation. You condition on the hidden variable I, the latent variable I, and you look at the second moment for that Gaussian. And we have shown that for every Gaussian, the moment is, second moment is mu I transpose plus identity. You take the sum from I to k. Right, so and then this is 1 over k times sum of, basically this is the average of the outer product of mu I transpose plus identity. So the question becomes, suppose you just want to use the first moment and the second moment. The question becomes, can we recover from M1 and M2? Right, so, or maybe more specifically from the average of mu I and the average of mu I transpose. So, and the claim is that this is not possible. At least when k is larger than 3. So there are two kind of arguments. I guess there's one argument. So the argument is the following. The reason why this is not possible is that these are just not enough information for you to recover in some sense. So there's like you're still missing some kind of like rotations, missing the rotation like the information. Okay, what does that really mean? Let me specify. So suppose you, just to make the discussion easier, let's define U to be this collection of the means, mu1 up to mu k, which is in dimension d by k. So this is the matrix you want to recover, right? So, and I'm claiming that there are going to exist two set of mu's that have the same average like the same quantities here. These two quantities, the both of M1 and M2 are the same, even though the mu's are different. I'm going to construct such a situation. How do I do that? I'm going to take a rotation matrix R in dimension k by k. I'm going to rotate. So basically, I'm going to consider U versus U times R, right? If you rotate on the right-hand side, you got a different type of set of means. So I'm going to claim that U and U times R have the same statistics, have these same two quantities. So first thing is that if you look at the average of the outer product, mu I transpose. Sorry, this is 1 over k. Then this is 1 over k times U transpose in our simplified notation. And this is equals to 1 over k times UR transpose. It's just because RR transpose is equals to identity. That's the definition of rotation matrix. So that means that U and UR are not distinguishable from this quantity, from the average of the product of U and the mu and mu I transpose. So and now let's look at the first order moment. So to make the first order moment also not distinguishable, I also have to take in addition R such that R times all1 vector is still equal to all1 vector. So you want a rotation such that you want a rotation, but you don't want to rotate the direction of all1 vector. That's easy. You have so many rotations, right? You just want to say I'm going to rotate. It's kind of like if you have a globe, you have one direction which you don't change, but you can rotate still in other d-2 directions. Right? There are still k-2 directions, right? Because dimension is k here. So you still have a lot of degree of freedom to choose many different R's that satisfies this, as long as k is somewhat big, like larger than 3. So, and then suppose you satisfy this, then UR times all1 vector, or maybe let's write this. So 1 over k times sum of mu I, this is 1 over k times U times all1 vector, right? I'm claiming that this is equals to 1 over k times U times R times all1 vector, just because I design R like this. So that's why from this average column statistic, or from this quantity, you still don't distinguish U and UR, right? So U and UR are not distinguishable. Because they exactly match the first moment and second moment. So that's why we need to go to M3 to distinguish, to uniquely identify the columns of U. Okay, I think we are 5 minutes early, but I think the next thing would be probably takes much more than 5 minutes. So I guess I will just stop here to see whether there's any questions. And tomorrow, next lecture, we'll continue with solving this question with M3. Any questions? Yeah. So the question is, how do you infer the number of Gaussians? So first of all, you are right that in the formulation right now, I'm assuming I know exactly the number of Gaussians. I'm even assuming that I know all the probabilities for each Gaussian, right? P1 up to Pk are exactly equal to 1 over k. So, and the question is, how do you kind of like infer the number of Gaussians? Maybe also another question is, how do you infer the P1 up to Pk, right? So there are ways. Of course, there are ways depending on, there are various ways depending on what assumptions you make, but definitely it's possible. For example, one somewhat one way that would work in certain cases is that you can infer the number of Gaussians by looking at the rank of this matrix. Suppose you believe that all the mu i's are not kind of like degenerate. They are all in kind of like general positions. So then the rank of this matrix will be K, especially for K, when K is less than D, right? So then you can infer number of Gaussians K by looking at the rank of this matrix. So, but I'm not saying that's actually really a great method, because empirically you may got into other issues because maybe your condition is not exactly matched, so on and so forth. So there are many other ways, and the empirically the most kind of like typical way to estimate the number of Gaussians is using non-parametric Bayesian methods, which I guess is not something we will cover here. So for the theoretical setup, we are mostly interested in the cleanest setting where you know everything, and it's still an open question to recover the mu i's even with the knowledge of the number of Gaussians. Right. So as long as that happens, it wouldn't work, right? So that's why it's probably not a great idea. But actually, typically, if you really look at the high-dimensional data, the mu i's typically they are independent. So, but they could have some kind of like one of them could live in approximately the subspace of the others. So then it becomes tricky because whether you are robust to error, so on and so forth. Yes. So I think loosely speaking is reasonable, but if you really look at the details, it's not that great. So that's why you need other methods sometimes. Okay, I guess if there's no other questions, I will see you next Monday.